In chapters 5 and 6, we looked at how to use the hardware renderer to create elements from pre-generated images such as smoke and dust. The hardware renderer, however, is limited by Maya's use of OpenGL with respect to textures and alpha channels. Procedural shaders that need to be generated from scratch tend to be quite difficult if you're hardware rendering. Software rendering picks up where the hardware renderer leaves off. In this chapter, we're going to look at how to create a fire effect using software cloud particles. The fire is generated procedurally, so we have control over the density, color, and speed of the texture while maintaining control over everything we covered in previous chapters, like per particle attributes. Output resolution and media type play heavily in deciding on the look of our final render. What may look good at 320 by 240 in a test render may not have enough detail for a full-res 2K image. Also, color temperatures and glows must be considered if outputting to film due to the nature of film transfer and projection techniques. Talk to an experienced compositor before you start developing the final look of your elements to avoid any unexpected results in the final product. Applying procedural textures to particles can be tricky. Changing small aspects of your simulation, such as the radius or position of texture placement nodes, can make a huge difference in the look of your effect. Keeping your shaders look predictable requires a lot of patience and careful tweaking. I've found it imperative to keep notes of each attribute you change in each version of your file. Sometimes, making small tweaks to only 2 or 3 different attributes can give you an entirely different look. I've opened up the file ch7 handfire base in the scenes directory of my Maya project. The animation's 96 frames long. If I play through the entire frame range, you'll see a hand which has been animated with a skeleton, then baked into a blend shape. In a production environment, development of the fire effect might take place at the same time as the hand's animation, so I would simply substitute the final animated geometry for this one when the particle's look is finished. I've added a simple surface emitter to the hand with animated rate and speed channels. There's also a few minor tweaks to the emitter, such as to the speed random and normal speed attributes. The particles have their inherit factor attribute turned up to 0.2, so they adopt some of the hand's movements. Maya's cloud-type particles have no usable blobby-like thresholding, so the trick to realistic fire in Maya is keeping the particles clumped together. For this effect, I'm controlling the particle's opacity based on how far away it is from the center of the hand's bounding box. This technique somewhat echoes the behavior of real flames. When fire moves away from a source of fuel, it dies off. First, let's give the particle some direction away from the hand. I've made this sphere above the hand a goal object for the particles, and I'll add a goal PP line in the particle's creation and runtime expressions using the same techniques you saw in Chapter 6. Each particle's goal PP ramps up as the particle ages. I've also modified the particle's lifespan PP and mass attributes. The lifespan of each particle is important to keep the size of the fire effect down. I tend to think of lifespan dictating the scale of my effect rather than simply how long each particle lives. If most particles die off before they reach the top of the screen, the effect will seem contained, but if the particles pass through the top of the frame, the entire image will be filled with flames. I've made the particles heavier by adjusting their mass attribute. This helps keep the particles under control when we add high-frequency turbulence later on. I want the particles' incandescence to be brighter when they're born, so I'm going to add a vector per particle attribute. We'll create an incandescence PP as well as an init incandescence PP attribute, so we can use a smooth step technique to ramp it in. Note that these are vector attributes. They have to contain red, green, and blue values for each particle. I've also added a float attribute to the particle shape called incandmult, which will act as a multiplier to each particle's incandescence. I'll set this value to 5. This means that some particles' incandescence values will be greater than 1, which will give the fire a blown-out look when it's born. Be careful not to set this multiplier too high, or you may see some clamped color values in your final rendered image. Notice how I've randomized the particle's incandescence. I did this by choosing a basic blue color, then varying the value in a rand function when declaring the vector. When the particle is born, I want it to have the full incandescence value, then fade back down to its normal level. This all happens within the first 40% of its life. I've added a clamp function to make sure that the particle's incandescence multiplier never drops below 1 or goes above the main multiplier value. I'm going to add some standard opacity and radius control in my expressions so the particle's birth and death values are handled nicely. As I mentioned before, the best way to keep the particle cloud in one central mass is to change each particle's opacity based on how far it is from the hand. In order to do this, I first need to calculate the center of the hand's bounding box in the x and z axes. I'm going to do this in an external expression, which evaluates only once per frame, rather than in the runtime expression, which calculates once per frame for every particle. Here, I've queried the bounding box of the hand and averaged the min and max values in the x and z axes. I then assigned those values to global floats. I have to use global variables here so the runtime expression can read them in. In the runtime expression, I first import the global variable, then extract the particle's position in x and measure the distance between the two. By using the absolute value function, I force the result to always be a positive number. Finally, I use a smooth step with a min and max distance technique, which reads two float attributes on the particle shape, called inner opaque and outer opaque. This result multiplies the particle's opacity at the end of the runtime expression after all the other opacity calls have been made. In other words, if the particle's distance in x from the center of the hand is greater than 2, its opacity is 0. If it is less than 0.5 units from the center of the hand, it gets its full opacity assignment. This is easier to see if I reduce the inner opaque to 0 and the outer opaque distance to 1. I've used the same turbulence techniques I showed you in Chapter 5, where I have one small and one large frequency turbulence. The large turbulence has its phase animated with an expression, as you saw in the tire smoke file. I've also created a drag field with a magnitude of 0.5 to slow the particles down. All of these fields have their attenuation set to 0. The main fire doesn't collide with the geometry, it goes right through it, which is sufficient for this effect. I want to create a second layer of fire which lies close to the hand's surface. To achieve this, I've created an emitter inside the base of the hand, which emits particles that collide with the geometry. The way the particles stay stuck inside the geometry causes the fire to appear as if it's crawling over the surface of the hand. The emitter follows the hand through an expression. Here, I'm querying the position of a specific vertex at the bottom of the geometry. I'm using the vertex's y value, as well as the center point x and z variables to move the emitter around. I'll duplicate the original fire particles, making sure Duplicate Input Connections is turned on in my preferences. This brings over my creation and runtime expressions to the new particle object, as well as any custom attributes I've created. First, I have to make sure all my polynormals are facing in the correct inward direction. Mixed polynormal directions with particle collisions can sometimes give you unpredictable results. I'll now set these new particles to collide with the geometry. I want to give the particles a bit of a bounce, so I'll set the resulting GeoConnector's resilience attribute to 0.2. I don't want any friction, so I'll set it to 0. Finally, I'll tell this new particle object to emit from my internal emitter and not from the main emitter. The internal particles have creation and runtime expressions almost identical to the main fire parts, except for a longer lifespan and smaller radius. The internal emitter is also spitting out more particles than the main emitter. Once I'm satisfied with the movement of my particles, I'll cache the data so I don't have to constantly evaluate my scene. Remember, if you change anything about your runtime expressions after you've cached your particles, the changes won't take effect until you recache. All per particle attributes, including any custom ones, are cached. You'll notice cloud-type particles show up as simple circular sprites. A small amount of their per particle data, such as their radius and opacity, are displayed in hardware. Other than that, you'll only see gray circles when you view your particles in shaded mode. Let's move into building a shader for the particle fire. I'm going to start off by creating my own particle cloud shader, which is under my volumetric materials list, and assign it to my particle object. The particle cloud shader is the only shader available for use with cloud-type particles. It has a few different properties than a regular surface shader, the most obvious of which are these life color, transparency, and incandescence attributes. People typically connect ramps to these inputs. The ramps run through the particle's birth to the end of its lifespan, changing values as it goes along. We, however, want to use our per particle attributes for transparency, which we call opacity, and incandescence. Ramps don't allow as much control over individual particles' values. The same ramp is used for each particle, no matter its radius, position, or velocity. The way to access per particle attributes in the software renderer is to use a particle sampler info node, which you can plug into your particle cloud shader. I'll create one for both transparency and incandescence. In this case, there's nothing to set in the node once it's created. All it does is read each individual particle's requested attribute for use in the software renderer, depending on the shader attribute you assign it to. For example, connecting the particle sampler info node to the life transparency of my particle cloud, each particle's opacity pp attribute will be read when the renderer is invoked. Life color reads RGB pp, life incandescence reads incandescence pp, etc. You can use this node to drive other vector or float attributes of your particle object. The unique thing about the particle cloud shader is that color has little influence over the look of your particles. I tend to assign textures to the blob map attribute and give the shader a simple solid color. The blob map is where all the control lies, giving the particle cloud much more depth and transparency than if you had used the standard mapping attributes. I'm going to set my color to a simple blue, then attach a 3D cloud texture to the blob map. I like using the 3D cloud texture for elements like this, as it gives you control over the edges of your flames, as well as lots of other controls that help move the fire around. The scale of your scene, the radius of your particles, how fast they're moving, and other factors all affect the way the 3D cloud shader looks. I'm going to input values that work in this particular scene. This fire will emulate a kind of alcohol flame, so it will be mostly blue. I'm going to make my two colors light and dark blue. I'll use the blue from the color attribute of the particle cloud shader for color 1 and use a similar but darker blue for color 2. One of the tricks that makes a cloud texture look like fire is its high contrast, so not only will I change the contrast attribute to 2, but I'll also raise the amplitude to 6. You can immediately see the difference in the texture sample. If you're familiar with the way fractional Brownian motion is structured, you should recognize some of these attributes. Depth is essentially the min and max number of octaves. Amplitude can be equated to gain. I want very fine detail in my fire, so I'm going to set my minimum depth to 2 and my maximum depth to 6. The higher the max depth, the more fine detail my fire will have, although it tends to get noisy after 6 or 8 iterations. Other attributes I'm going to set are edge and center threshold and transparency range. These attributes control the outer and inner edges of the particle cloud's texture. I've set these values so that my edges are brought in a bit and made to look a bit more contrasty. The last cloud attribute I want to change is the ratio, which controls the frequency of your cloud noise. It's very sensitive. I've found ranges between 0 and 1 to be sufficient for most effects. I'm going to use a value of 0.55. I'll also increase the density of the cloud to 1.5 and set the roundness to 0.5, giving the particles a bit more irregularity in their shape. I'll also turn off Maya's built-in noise for the particle cloud shader, as we're providing our own. If I render the scene now, my particles will have a soft, cloudy look to them. This, of course, is not what we need for a fire effect, which has sharp edges to the licks of flame, as well as internal detail. Here's what the particles look like so far. Notice the particles don't seem to have any direction. I can control this look as well as the scale of the effect by changing the size of the 3D Cloud's Place 3D Texture node. I'm going to scale it down overall, then scale it up in the y-axis to make the particles look as if they're streaming upwards. I'm also going to move the placement node to the approximate center of the particle object, so I can see its scale and movement as I'm looking through my camera. Looking at a second render, I see my fire is all streaming in the exact same fashion. I need a way to warp the space within the 3D Cloud texture. This is where the 3D Cloud's ripple attribute comes in. It's best to connect a 3D texture to this attribute, so as the particles move through space, the texture gets distorted. I'm going to connect a Brownian texture to this attribute, which is a similar noise function to the 3D Cloud texture I'm already using. I want to distort the shader only slightly, so I'll make the Brownian's lacunarity and octaves less than Maya defaults. Also, this Brownian appears to have too little effect on my 3D cloud, so I'm going to increase its color offset to 50% gray, which brings up all the Brownian's values. Looking at another render, I see my Brownian warping the 3D cloud texture nicely. The fire is still lacking some hot spots or areas of greater intensity. I'm going to add another Brownian node to my shader, this time to the color gain attribute of the 3D cloud texture. This will give me hot and cold spots throughout my fire, which I refer to as subnoise. As with the previous Brownian, Maya's default values are a bit off for what we need. I'm going to give this Brownian more contrast and detail. Also, I want to pump this Brownian's values way up to give the fire some real bright spots. I'll do this by forcing its color gain to 2.0. The size of this Brownian's texture placement node is very important. If I were to leave it at its default scale, my subnoise would be too small and spotty. I want my subnoise pattern to echo the 3D cloud's vertical streak pattern. I'm going to change the size of this texture placement node to approximately the same ratio as the 3D clouds, but on a much larger scale. Another render shows us some fairly nice-looking flames with interesting edge density and color falloff. If I render a sequence of images now, my particles would appear to move through the texture. I find it necessary to animate my texture placement nodes along with the movement of the particles. I've already animated the main 3D Cloud's texture node by moving it up slowly in the y-axis. I've done the same with the subnoise's texture. Because the particles are already moving upwards, I only have to move these placement nodes slightly to get a decent vertical crawl to my fire. I can add even more variation to my cloud's noise by rotating it as it slides up. I'll add an expression to the node's Y and Z rotations. To create a nice random smooth noise for the node's rotations, I've simply added a few sine functions together, each offset by a different amount. I'll also apply the same type of movement to the rotations of the main Brownian. This will shift the cloud's ripples around in space, giving variation to the 3D cloud's frequency. For some further variation, I'll create a second identical fire shader and assign it to the inner fire. Then I can modify the expressions to give the inner fire a slightly different look. Now, all I have to do is create a black material for the hand, making sure to set its matte opacity to black hole, and I'm ready to render my element. My final frames for the fire element took about 10 minutes each to render at NTSC resolution.